block of material, we will be looking at a different way of describing data. We'll be describing data using summary measures. But first of all, I want to back up and take a look at the whole question of numeric descriptive measures. Why are they so important? We've spent time studying graphical ways of looking at things, and if you'll remember from that discussion, there are some advantages to a numerical measure. One is that they are precise, they're objectively determined, and they really help us describe in a very specific way what's going on in certain measures of our populations and samples. And we can contrast that to the graphical measures, which gave us a really quick snapshot, but sometimes were a little bit difficult to compare because they're somewhat subjective in terms of how we are interpreting them. The numerical measures are precise and objectively determined. They're also easily manipulated arithmetically and easily interpreted, and again, easier to compare than graphical displays of data. Because they're numerical and we can do calculations on them, it permits a more detailed analysis of the data sets, and we'll rely on that very heavily when we get down towards doing inferential statistics later on in this course. Well, as we said, I think at the very outset of our discussions, this whole concept of quantitative analysis involves a type of language, new sets of terminology and new sets of symbols. And there are two types of symbols that we use that we'll see pop up throughout this course. And these are symbols for some of these summary measures. And they vary depending on whether we are trying to represent a measure for a population or for a sample. And we'll make a greater distinction between populations and samples, again, as we get further down the road towards doing sampling and inferential statistics. But our population parameters are usually represented by uppercase English letters or lowercase Greek letters. Our sample statistics, the measures we take on a sample, are represented typically by lowercase English letters. And I've provided for you here a list, a table of some of the most common measures that are taken on populations or on samples and the symbols that are associated with them. So when we take a measure on a population, we call it a population parameter. And that could be the mean of the population, the median, the variance, etc. If we take that same measure but on a sample, we call it a sample statistic. And as you can see, different symbols are used for each of those. So for the mean, for example, we use the Greek symbol mu for the population, yet for a sample, we say x bar. If our variable is x, the mean of x we call x bar for a sample. And so on. And you can go look down this table and see some of the very common measures that are taken. We may just count the number of observations. We can take the mean, the median, the variance, standard deviation, correlations, proportions, and these are just a sample. And we'll talk about several of these, and we'll see them pop up in formulae and mathematical expressions as we proceed through the course. So with that introduction, let's go ahead and take a look at the central location. Where are the values most tightly clustered around? They tell us in one way or another where the center of the data is located. I put center in parentheses here, in quotes here, because what exactly do we mean by center? It turns out we can interpret that a bit differently. And there are three very common measures that are used, and they treat center entirely different from each other. And those measures that are used are the mode, the median, and the mean, the arithmetic mean or the average. And we'll look at each one of those in turn. Firstly, what do we mean by the mode? If I have a set of data, a set of values or observations, and I ask for the mode or the modal value, what I'm looking for is the most frequently occurring observation. And this represents, if we were looking at a histogram of this data set, the location of the greatest clustering. And you'll remember from our discussion of histograms that it's possible to have multiple modes. We can have a trimodal or bimodal distribution, meaning that there are 3 or 2, respectively, areas of clustering, distinct areas of clustering. This idea of the mode can be used both for quantitative and qualitative data. We can have the modal value in a quantitative data set or the modal category in a qualitative data set. And you'll remember again from histograms, when we took our numerical data and broke it up into intervals, in essence, we were creating categories or bins, ordinal categories. And we talk about the modal bin or the modal class or interval. So the mode can be used for both qualitative and quantitative data. And if in Excel I have a column with my observations under a certain variable, I can use this formula to calculate the value of the mode. In Excel, I can just go to a particular cell and type equals mode, and then in parentheses I select my data set, or perhaps I type in a label that I've created that refers to my array of values in which I want to find the mode. And this will return the modal value in that data set. So the mode is fairly straightforward. And let's now talk about the median, which takes a look at the center of the data in a different way. So the mode thinks of things in terms of what's the most frequently occurring observation. That's the modal representation of the center of the data. What about the median? The median takes a different view. It represents the middle value in a series of observations if they're arranged in order from low to high. I think of this sort of as the geographic center. The idea is I need to have an equal number of observations above or below this median value. And in Excel, again, I can calculate this using the formula equals median, and then in parentheses I select my data set. Now the calculation that's done here is slightly different if I have an odd number of observations or an even number of observations. Because you'll remember the idea is to find a value such that I have an equal number of points on either side of that median value. But if my total number of observations is odd, then that median value is just going to be the middle value. For example, if I had 101 observations in my data set, well, I need to have the same number of observations above and below my median. So if I arrange them in order from low to high or high to low, my 51st value would be that value that had the same number of observations on either side, 50 above and 50 below, plus my middle value, 101 total observations. So that middle value would be the median if I have an odd number of observations. But what about if I have an even number of observations? Suppose instead of 101, I had 100 observations. Well, what the median becomes then is the average of the two middle values. So I have my data arranged from low to high. If I have 100 observations, I need to have an equal number on either side of my median. So that'll be 50 below and 50 above. Well, I take those two middle values, the 50th and the 51st values, and average those together. And that will return the median value in the data set. So they're two slightly different calculations depending on whether the value is either, the number of observations is either odd or even. And as it turns out, only the middle point, if I have an odd number of observations, or the middle 2 points, if I have an even number of observations, actually play a role in the numerical value of the median. The values of all the other points in the distribution don't come into play in that calculation at all. And this is very important for deciding whether or not the median is the best measure that we want to take. The median, because no other points except for the central ones are involved in the calculation, are not influenced by extreme values. What's happening out at the very high end or the low end of the distribution really does not impact the value of the median. The third measure is actually the most common measure, and it is called the arithmetic mean or the average. It's the most popular measure of central location of a data set, and it's the most useful in that we're going to rely heavily on this one when we're doing inferential statistics and estimation. So it's called the mean or the average, And it's what we usually think of as an average. We sum each of the values and we divide it by the number of observations. And we can represent this in symbols by what's equation 3.1 in our text, which says that x bar is equal to the sum of all of our values of x from the first one to the last, our nth observation, divided by that number of observations, n. And you'll notice from the symbols here that this formula would be referring to a sample. I've got x bar, lowercase n. So those would be the symbols for sample statistics. But yes, this is simply what we would think of as an average. We're going to sum each of our values and divide by the number of values. And that's how we calculate the arithmetic mean. And I like to think of this as representing the balance point of the distribution. That's sort of the way it represents the idea of being at the center of the distribution. If you can imagine a histogram that you've generated for a certain distribution, if you could lift it off the page and balance it at some point along that x-axis, along the horizontal axis, well, that point where that histogram would exactly balance, that would be the mean of the distribution. And because of the way the mean is calculated, its actual value is influenced by every single value in the distribution, because they all are summed together in the numerator. And as a result, unlike the median, the mean is influenced by extreme observations. So the values at the very high end, the values at the very low end of the distribution, every value is actually playing a role in the numerical result of the arithmetic mean, or the average. Another way of thinking about this mean, if you think about the balance point, the mean is that point where the sum of the deviations of every point in the distribution is exactly equal to 0. Now, the deviation is the distance that each point is away from the mean. So points above the mean are going to have positive deviations, and if they're just a little above the mean, their deviations will be small. If they're far above the mean, their deviations will be large. Same for points that are below the mean, except that those deviations will be negative. Well, the mean can be thought of as that value where those deviations exactly balance out. Again, it's that balance point. So the sum of all those deviations is going to exactly equal 0. The positive ones will balance the negative ones, and the sum, again, of those deviations will be equal to 0. Just another way of thinking about this concept of the balance point. And in Excel, the formula that we use this time isn't the word mean, but the word average. So if I want to calculate the average of a list of numeric values, I say equals average, and then in parentheses I have my array of values, and that will return for me the arithmetic mean, or the average of all those values in the data set. We've introduced 3 different measures of what's the center of a data set. And when would you use what? Well, it turns out the mean is used most frequently. It's used in all inferential statistics, and especially in cases where we are very interested in including the impact of outliers, of values that are far away from that central location. The median, by its very nature, does not include outliers, and sometimes that's what we want. Sometimes we don't want to include the values that lie far away from the center of the distribution, especially if those outliers are predominantly on one side of our distribution. And then lastly, the mode. Well, when all we're interested in is the most frequently occurring value, the mode is the way to go. And when we talk about qualitative data or categorical data, the mode really is our only option, because its mean and the median don't really apply to qualitative data. All right, well, that wraps up our discussion on the 3 main measures of central location that are commonly used. We'll pick up with a discussion of some other very important summary measures that are used to describe data.